All right, y'all. In this video, we're going to start Unit 10, and this unit is over counting and probability. It's going to be a little bit of a change of pace from normal algebra stuff. Talk about a little bit more real-world things. We'll start out with counting, so trying to figure out how many different ways something can happen, and then later on in the unit, we'll move into probability and think about, what's the chances of this thing happening based on how many different ways this thing could occur, and what are we trying to figure out, and all that good stuff. And we'll even end the unit talking a little bit about expected value, which you can apply to a lot of games and thinking about, if I play this game, what's my expected outcome if I play this game a bunch of times. So we'll get into some more real world stuff and move away a little bit from algebra. So today we're going to start out with counting principles. And so counting principles in this, what we'll be talking about is just starting the discussion about how many different ways can I do some given scenario. And we'll get more in-depth in section 2, where we'll talk about permutations and combinations. Maybe those are words that you've heard before, but if not, that's okay. Today we'll start out with some really, really basic stuff, and then we'll get to some more difficult things as we go. So first of all, a subset is a set that can be made from all of the elements of another set. So for example, here's some subsets of 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, we call those things elements. These are all elements of the set. And so a subset is any smaller set or of the same size set that you can make out of these elements. So, I apologize. So for example, some subsets could be, I could have just the set itself. And this symbol that I'm using here to start and end the set is called a brace. So one subset of 1, 2, 3, 4, 5 is actually the set 1, 2, 3, 4, 5. I could have this symbol right here means an empty set, which means I have a set with nothing in it, and then I have a bunch of other sets that I can make, like for example 1, 2, 3. I could do the set 1, 2. I'll mention this in a second, but order does not matter in a set, so you could have something like 5, 3. You could have something like just the number 2, etc. So all these things are what we call subsets, okay? One thing to keep in mind, I just said this a second ago, is that in a set, the order does not matter. So in other words, there's no difference between 5, 3 and 3, 5. These mean the same thing. All it matters is what's in the set, not the order that it appears in the set. So to help us figure out our first counting principle, let's try this. So if we wanted to write out all the subsets of just the letter A, okay, sorry. All the subsets of just the letter A. Well, there's two subsets that I could come up with here. I could literally just write A, okay, or I could have an empty set, which is a set with nothing in it, okay? So in total, there are two subsets here, all right? Okay, let's move on to the next one. Let's write out all the subsets of A, comma, B. Well, start out same way here. You could have A, comma, B, okay? So you can just write out the whole set. You could have an empty set with nothing in it. Then you could also make a set with just A, and then you could also make a set with just B. All right, and I think that's everything that we can get here. So in this case, there would be a total of 4 subsets. Okay, you got the whole one, you got an empty set, and you got one set each for each letter. All right, let's do this one more time. Let's see if we can see a pattern emerging. So now let's write out all the subsets of A, B, C. So just follow the same structure here. We could have A, B, C. Okay, we could have an empty set. We could have a set with just A, set with just B, a set with just C. But then we could also have some sets where we have just 2 of these letters, right? So I could have A and B. Now again, some students will try to write down B, comma A as well. But again, in terms of sets, these are the same thing. So we wouldn't want to write that down. That doesn't give me any new set. I could do A, comma C though. In any order. Or, last but not least, I think that covers everything that I could get with A. I could also have B, comma C. Okay? And I believe these are all the different subsets that I could come up with here. Subset with 3, a subset with nothing, 3 subsets with 1, and then 3 subsets where we have 2 elements each. Okay, and if we count these up, we've got 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so that gives us a total of 8 subsets. All right, so if we think about a pattern maybe emerging here, what you'll notice is that in this first example, when we wrote out all the subsets of just A, there was one element and there was a total of 2 subsets. This is 2 to the first. In this one, in the next one, we had 2 elements, a comma b, and we got 4 subsets. That's the same thing as 2 squared. In the next one, we had ABC, so 1, 2, 3 elements, and there were a total of 8 subsets, or 2 cubed. So if we think about this, if we wanted to come up with a counting principle, we could say, in general, from a set with n elements, okay, from a set with n elements, and again, elements are just however many things are in, or the items that are in the set. So from a set with n elements, we can create, you see a pattern coming up here, 2 to the n subsets. Okay, again, all of these, if we wanted to figure out how many subsets we could make, we just looked at how many things were in the set, and we raised it 2 to that power. So real world example here, Mr. Griffith has 7 students in a class. How many groups of students could he make if the number of students in each group could vary? And again, if we're talking about a group here, the order of the group does not matter. We're just talking about who's in the group. So we could go anywhere from having no students in a group all the way up to having 7 students in a group, and then any number of students in a group in between. So how many groups of students could you make if the number of students in each group could vary? Well, this fits into our pattern here. Instead of me listing out all possible groups, what I could say is, well, there are 7 students. Okay, so this is like 7 elements. So to figure out the number of subsets or groups that I could make, it would just be 2 to the 7 groups. And if you do this on a calculator, which would be fine, that means we could make out 128 groups. Okay, 2 to the 7th is 128. So obviously, knowing this counting principle is a lot easier than me having to write out every single possible group. All right, so there's our first counting principle of the day. All right, let's move on to our next one. This is a pretty common problem. Even in middle school, you might have seen some problems like this. There's something that we're going to draw to help us figure out this problem. Let's read it first. It says, in a group of 200 people, 105 have traveled to Canada, 73 have traveled to Mexico, 50 have traveled to both Mexico and Canada. So what we're going to do here is, to help describe this situation and give us a visual, we're going to create what we call a Venn diagram. I'm going to call the right side of this, Mexico, call the left side Canada. And where I'm actually going to start here is in the middle, which is this intersecting region of the Venn diagram. So anything that goes in this intersecting region means that it applies to both the Canada and the Mexico category. So if we're looking at where in this sentence we would get this information from, we would have to look at the end where it says 50 people have traveled to both Mexico and Canada. So what that means is I'm going to put a 50 in the overlapping region here. These are the people that have gone to both countries. Okay. Now in these circles, this one right here and this one right here, we're going to put the people that only apply to either just the Canada category or just the Mexico category. Now we got to figure out what those numbers are. So let's start with Canada here. It says 105 total people have traveled to Canada. Well, we have already accounted for 50 of those people here in the middle of the Venn diagram. So to figure out how many people went to just Canada, I would have to do 105 minus 50. Okay, and that would give me 55. So I'm going to put 55 people here in the only Canada category. And if I think about 73 have traveled to Mexico, well, 73 minus 50 is 23. So that means there's got to be 23 people that have only been to Mexico. Now, let's jump into our first question. We now have a Venn diagram describing this scenario. The first question says, how many people have traveled to Mexico or Canada? And this word right here, or, throws off a lot of students. So let's think about this. I always tell students, when you get confused with the words or and, just go back to a common sense scenario and think about how you would answer it, because these do pretty much fall into common sense categories. So let's say you're watching this video and you have traveled to both Mexico and Canada. Okay, so you've been on a vacation to both of those places at various points in your life. If I walked up to you right now and I said, hey, have you ever been to Mexico or Canada before? You would not answer that question with a no if you've been to both countries. You would be like, yeah, I've been to Mexico or Canada. I've been to both of them. Okay. So oftentimes when I get this question at first, what students will do is they'll be like, Mexico or Canada. Well, it can't mean both. So the answer must be 55 plus 23. There's 55 people that have been to Canada and 23 that have been to Mexico. But if this is all you do, what you're doing here is you're leaving off the people that went to both, which would still fall into this category of having been to either Mexico or Canada. So if I wanted to figure out how many people have traveled to Mexico or Canada, I want to talk about the total number of people that have been to just Mexico, the total number of people that have been to just Mexico, which would be 23, plus the total number of people that have been to just Canada, which is 55, plus the total number of people that have been to both. And when I add all these together, I get 105 plus 23, which is 128 people. Okay, so there are 128 people that have been to either Mexico or Canada, or, as we said, both, which falls into this category as well. All right, now if we go to letter B, how many have traveled to neither Mexico nor Canada? Well, just got to go back and look at the beginning of the problem here. There's 200 people in the group. We just figured out 128 people have been to at least one of these countries. So if I subtract off that 128, that means there's got to be 72 people that have not been to either one. Okay. So once we get this picture of this Venn diagram, we can answer these questions. Now, this next counting formula that I'm going to write down here, this is something that some students just completely ignore, and that is perfectly fine. Because if you draw a good Venn diagram, you don't really have to think about this formula, but I'm going to write it down anyways for the sake of notation. And if it is something that you want to memorize, you can do these problems really, really quickly without a Venn diagram. So based on our last example, here's our counting formula. N, which stands for the number of A union B. Okay, so just notation and vocabulary wise, this little symbol right here means the union. And another way of thinking about union is or. So in other words, this means the number of people that fall into either category A or category B. Okay, and this is equal to the number of people or the number of elements in category A. So we'll write a little note here. N of A just means the number of elements in category A plus N of B, so the number of elements in category B, minus the number of elements in A intersect B. Okay, again, vocabulary wise, if you ever see an upside down U, this stands for intersection. Okay, and another way of thinking about intersection is and. Right, and students, if they ever ask me or they're trying to remember what intersection means, well, just think about what an intersection literally means. It means where they cross. So that would be things that fall into both categories. So if you apply this to our last example, okay, if you think about A as being the number of people that have been to Canada and B as the number of people that have been to Mexico, let's see if this counting principle applies. So the number of people that have been to Canada or Mexico, if we start out with the number of people that have been to Canada, the problem told us that there were 105 people. Okay, so this would be 105 plus the number of people that fall into category B. So this would be the number of people that have gone to Mexico. That would be 73. Minus the number of people that have been to both A and B, which means the number of people that have been to both Mexico and Canada. And we saw in the problem here that there are 50 people that have traveled to both. Okay, so basically what we're doing here is we're taking the number of people in A and the number of people B, and then we're subtracting the overlap. And if you do the math here, 105 plus 73 is 178, minus 50 is 128 people. And that agrees exactly with what we got when we did our Venn diagram. Again, you don't need to remember this counting principle if you don't want to. I'm not going to ask you to write down this formula at all. It will kind of come back into play when we start talking about some probability. You'll see a formula that's pretty similar to this, but even in that scenario, it's not a formula that you're going to have to memorize. You can always go back and use common sense or a Venn diagram to get the job done, but it is here nonetheless. All right, we got one more counting principle to cover. So this says, Mr. Griffith is trying to figure out what to wear to school tomorrow. Assume, of course, that all the different outfits he can make would match perfectly, so we don't have to take into account colors or any of that stuff. So we have 3 shirts, 2 ties, and 2 pairs of pants. List all the different outfits that he could wear. This is a fairly common SAT type question. We're going to start by doing this the long way, and then we'll see if there's a pattern that emerges. And some of you guys might already know this pattern, but I'm going to begin by doing this the long way with a tree diagram. Okay, so if you think about a tree diagram for this, let's start out with the shirts. So with the shirts, I have shirt 1 that I could use. I have shirt 2 that I could use, or I have shirt 3 that I could use. Okay, pretty straightforward. All right, now next up, let's go to the ties. Now branching off of each shirt, I have two options for ties. I could either wear tie 1 or tie 2. Okay, so I could go shirt 1, tie 1, or I could go shirt 1, tie 2. I could go shirt 2, tie 1, shirt 2, tie 2, or I could go shirt 3, tie 1, or shirt 3, tie 2. Okay, so if you think about it at this point, we have 6 different outfits. Okay, but we've also got to take into account our pants. So let's do that as well. It says that there are 2 pairs of pants. So that means branching off of each shirt tie combo, I also have 2 pants combos. Okay, I've got pant 1 or pant 2. So I could go shirt 1, tie 1, pant 1. I could go shirt 1, tie 2, pant 1. I could go shirt 1, tie 2, pant 2. You can kind of see a pattern here. Pant 1, pant 2, pant 1, pant 2, pant 1, pant 2, and last but not least, shirt 3, tie 2, pant 1, or shirt 3, tie 2, pant 2. Okay, so you can kind of follow the patterns here. We are listing out all of the possible outfits, because if I want to just pick an outfit randomly, I could do shirt 2, tie 2, and pant 1, for example. Or I could do shirt 1, tie 2, pant 2, for example. Okay, but any combination that I see here would be outfits. And the question says to list all the different outfits that we could wear. And if we think about it, how many different outfits are there? Well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so there are a total of 12 different outfits. Okay. Now, some of you guys might be sitting here being like, Mr. Griffith, why did you do a tree diagram here? Because this is fairly obvious, and I already know this, and this is fine. What you'll notice is that there were 3 shirts, 2 ties, and 2 pairs of pants, and if you multiply all of these together, 3 times 2 times 2 gives me 12 outfits. Okay. And this makes sense. Say if you look at it, there's 3 shirts, and branching off of each shirt, there are 2 tie options, which means there are 1, 2, 3, 4, 5, 6, 3 times 2 shirt tie combos. But then branching off of each one of those shirt tie combos, there's also 2 pairs of pants. So I got to multiply all those shirt tie combos by 2, and then 6 times 2 gives me a total of 12 outfits. Okay, so this brings up a counting principle. We could say if there are in options in category 1, we'll say P options in category 2, Q options in category 3, etc. And to find total options, mathematically, we just do the number of options in category 1 times the number of options in category 2 times the number of options in category 3, ... Okay. I could have made this previous problem even more complicated if we would have added in socks, right? That could have been our category 4. So if I had said, hey, there was 5 different types of socks that you could wear, well, then we would have to take 12 and multiply it by 5 and so on and so forth. Okay, so you could have an infinite amount of categories here, but if we want to figure out the total number of options, we just take the amount of options in each category and multiply them by each other. Now, on to a real world example here. The last 3 characters in a license plate are, in this order, a number from 0 to 9, a letter from A to Z, and another number from 0 to 9. And the question says, how many different 3-character endings could the license plate have if, and this is important here, here's a restriction, if this first number of the ending cannot be an odd number. Okay. Well, this fits into what we were just doing. There are 3 different slots to fill here. I'm going to call this the slot method, and we got different things that we have to put in each slot. So anytime I see one of these problems, I like to start out by, I'm just going to put 3 slots. Okay, here's the first character. The first character has to be a number from 0 to 9 that isn't odd. And the reason why I'm saying that it can't be odd is because that last little bit of the problem there says the first number of the ending cannot be odd. Okay. All right. Next one says a letter from A to Z. Okay. And then last but not least, it says another number. Let's put a number that's not the first. That's not. Actually, they didn't give us any restriction on this, right? So I'm just going to put any number from 0 to 9. Okay. Any number from 0 to 9. Now let's clear this up real quick. I get this a lot where I say from 0 to 9. I've seen students get this wrong on quizzes and tests, and people are like, okay, well, 0 to 9, that's got to be 9 numbers. Okay, let's write all these out. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And if you count all these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10 numbers, not 9 numbers. Okay, so let's write down how many options we have in this first slot right here. So if we got to pick a number from 0 to 9 that isn't odd, well, remember, an odd number is something that cannot be evenly divided by 2. So that means I have to mark off 1, 3, 5, 7, and 9, leaving me with 0, 2, 4, 6, and 8. So that would give me a total of 5 options here for this first slot. Okay. All right, on to the next one. Letters from A to Z. Well, there are 26 letters in the alphabet. That's something we all need to know. And then last but not least, they didn't give me any restrictions on this last one, right? So any number from 0 to 9, and it doesn't seem like we can't repeat something, so that gives us 10 options. As we said, there are 10 numbers between 0 and 9, so if we want to figure out all the possible 3-character endings, we'd have to multiply them, and let's see, 5 times 26 is 130, times 10 is 1,300 endings, okay? Now, before we move on, I just want to, and you'll see this on the practice, I could give you a similar problem with a different outcome if I put some different restrictions, okay? So I'm just going to go ahead and address this here. Let's say that I had the same problem where same specifications for the first slot. Okay, the second slot can be any letter that's not a vowel. And then last but not least, let's save that for the final one. We can't repeat a number. Okay, so it's going to be any number from 0 to 9, but we can't repeat a number. Okay, so let's think. So for the first number, same specifications as what we had up here. So it's got to be a number that isn't odd. So we already said, hey, there's 5 options for that. Okay. If the second slot can be any number that's not a vowel, well, let's think about the vowels of the alphabet. A, E, I, O, U. We will not consider Y to be a vowel here. Well, that is 1, 2, 3, 4, 5. So if there's 26 letters and 5 of them are vowels, and those are not options, that means we have 21 options that are not a vowel. And this one's always a little tricky for students. So if we can't repeat a number for the last slot, well, let's think. We said that for the first slot, it can't be odd, which meant that we couldn't pick 1, 3, 5, 7, or 9 for the first slot. But let's say instead we picked one of these even numbers, and let's say, for example, that the number 8 got picked. Okay, well, once 8 gets picked, it's off the board, and then when we get to this third spot, all the other numbers are back in play except for 8, and so that would give us, well, there were 10, and we took one of them away, so now there are 9 options. Okay. And so when we're done, this should give me less options than what I had before, due to the fact that there's less numbers in each of those slots right there. And you can do this on a calculator. 21 times 5 times 9 gives me a total number of 945 3-character endings. Okay, so we can change these problems by changing some of the specifications. This is part of the critical reading of the problem. You got to figure out how many options each slot has. But once you do that, the rest of it's easy. You just multiply them all together. All right, that concludes these guided notes here. For the rest of class, you guys are going to work on some practice, and the sub has copies of that practice, and I'll put the solutions in the OneNote folder. Thanks, guys. Bye.